Hi everyone, welcome. We are starting on a new topic. The new topic is capacitors. So we want to start with a definition of what a capacitor is. Like we know, a capacitor is a device that is used to store electrical energy in the form of electric field. So that is why we are saying a capacitor can be defined as a device that is used to store electrical energy into an electric field. Having said that, we now want to look at what an electric field is, or rather an electric field patterns. The space around a charged body where the force of attraction or repulsion is felt is called electric field. So an electric field is the space around a charged body. If you have a magnet, for instance, if you have a magnet that is a north and a south, of course there will be some magnetic field. So the space around the magnet, the space around a charged body where the force of attraction or repulsion is felt is called electric field. Of course, later on we will be looking into magnetism. That is when we will explore this particular magnet. But for now, we are specifically talking about a charged body. A charged body. We move to the next point. The electric field is represented by lines along which the electrostatic force acts. These lines of force are called electric field lines. So we are saying electric field lines is represented by lines along which the electrostatic force of course acts. We now want to look at properties of electric lines of force. What are the properties? Number one property is electric field lines of force are imaginary lines. So we are saying they are imaginary because you cannot actually touch them. You cannot be able to see them. But because of science, we know they do exist. So they are imaginary. We imagine they exist. The second point is they start from a positive charge and end at a negative charge. They start from a positive charge and they end at a negative charge. Maybe that one I can illustrate it in this form, that if you're having a positive charge on this side, let us say this is a positive charge, and you're having a negative charge on the other side, then we will say the electric field, the electric lines of force will start from a positive and end to a negative. Just like we talk about current, which begins from a positive terminal to a negative terminal, the same case, the field lines of force, the lines of force, the electric lines of force begin from a positive charge to the negative charge. And that is why you will see, we'll be having something of this kind, like that, like this, because the lines, they begin from the positive charge, they end at the negative. So basically at the negative charge, the lines of force are entering. In other words, the electric field lines, they enter into the negative charge, but the positive charge releases. The lines of force are emerging out of the positive charge. So whenever you are given such a scenario, whenever you are given such a case, that is what will be happening, or that is the diagram you are expected. Sometimes you might find another scenario of this kind where you have a positive and you have another positive and another positive. So what we will draw is, we will say, because they are going to repel, you know, like charges repel and unlike charges attract. That is another property of lines of electric lines of force. Like charges repel and unlike charges attract. That is our last point in the notes. So we will say, we will draw it like this, like that, like this, like that. Remember we said, from a positive charge, the lines of force are leaving. So that is why you will draw it like this. The lines of force are leaving from the positive charge. They are leaving, they are leaving. And of course, you can put an X there to show that there is a force of repulsion. There is a force of repulsion. For this case, we have said there is a force of attraction because unlike charges attract. But for like charges, they repel. They are moving far away from one another. You can also have another case where you're having only negatives. So if you have a negative charge and you have another negative charge there, the same case applies. These ones now will be entering. They will be entering. So the arrows will be pointing inwards, meaning the lines of force enter into the negative charge. But for a positive charge, this is a force of repulsion. You draw an X to indicate that they are repelling from one another. They repel from one another. So basically, I've tried to elaborate number 2, which states that they start from a positive charge and end at a negative charge. So they start from positive, they end at the negative charge. I think that point is well understood. We move to the third point. Electric lines of force can never cross each other. Electric lines of force can never cross each other. You will never find a situation whereby you're having another one maybe moving in such a manner. These electric lines of force will never cross one another. They are parallel. In fact, if you have so many of them, they will be indicated in such a manner. Like this, they are parallel. There is no point, there is no given point where these lines are going to intersect. They are not going to cross against one another. They are parallel. So that point means electric lines of force can never cross each other. Can never cross each other. Number 4, they are closer where the electric field is stronger and spread where the field is weaker. So if you find these lines of force are very close towards one another, it means the electric field is very strong. But if you find the electric lines of force are spread, for instance, if you have such a case, whereby you have seen these fields are very close towards one another, this means that the force there, they are closer where the electric field is stronger and spread where the field is weaker. So it means if these lines of force are very close to one another, it means the electric field is stronger. But if you find they are spread, maybe you only have one there, another one there, another one there, the electric field here is weaker compared to this one. This has a strong field, this has a weaker field, because the closer the lines, the stronger the field. That is what number 4 means. Number 5, electric field lines of force always enter or leave the charged surface normally. They leave the surface normally, that is, they leave the surface at 90 degrees. So whenever this line leaves the surface, it leaves at 90 degrees. They leave at normal. So meaning the word normally, from the word normal, it means 90 degrees. In this case, it refers to 90 degrees. Meaning, whenever these lines are moving out of the surface, they move at 90 degrees. 90 degrees from the surface. The last point is, unlike charges attract, while like charges repel. I think we have explained that point. We now want to look into electric field strength. Look at electric field strength. So electric field strength electric field strength is denoted by letter E, and we can draw a figure that will illustrate that. If you have something of this kind. If you have two plates, like that, then you connect them against some voltage source, and let us say the distance of the two plates, the distance between the two plates, let us say that is D. D is the separation distance between this plate A, let us say this plate A, and this plate B. Plate B is connected to the positive terminal, plate A is connected to the negative terminal, and there is a space between A and B, and the space in between A and B is occupied by air. So we could say that the electric field will be directly proportional to the voltage, but it will be inversely proportional to D. Basically, remember, this experiment is set up to illustrate a capacitor. Remember, a capacitor is a device with two plates and some space in between them. So, and the function of the capacitor is to store charge. So, meaning, if the distance is very small, if the distance is smaller, it will be able to have a higher capacity to store charge. But if the distance is big, it will not have that ability to store more charge. That is why we are saying the charge stored by these two plates is dependent on the voltage. The higher the voltage, the more the charge this capacitor is going to store. And the bigger the distance, the smaller the charge that will be stored. So meaning the closer the plates, the higher the ability to store charge. But the far apart the two plates are, of course, the capacitance will reduce drastically. That is why we have this formula, that the electric field is directly proportional to the voltage, but inversely proportional to D. So in other words, we can say electric field is directly proportional to the voltage, but inversely proportional to the separation distance. Separation distance D. So this formula is very critical. You need to have it all the time, so that as we move ahead, we will be using it in a number of instances. It is very important for you to understand it. Another thing that as we wind up, another thing I just want to mention is another word for electric field. Electric field is also referred to as a potential gradient. So if you come across the word potential gradient, it means, or it is the same as the electric field. So an examiner can either give you potential gradient is 20, electric field is 20. Let it not confuse you, because they mean the same thing. So with those few remarks, we want to stop there so that we can meet in our next session. Thank you.